Stay.
So what's the funny?
No, it's recording, so stop swearing. Right, we'll see if this comes out. Right, do you want to grab a double page?
Yes, sir.
Do you want your favourite sofa?
Can you not just like turn that one page to the side?
Aye?
God, you walked by us class about 10 times yourself.
Do that.
always does it in this
He does a wee splash up computer, doesn't he?
Right. So, data representation, first unit that we've covered. Quite a few to go. Right, take me through it. What did we start off by learning about?
Binary.
Binary, awesome. So we talked about binary. What did we talk about with binary?
It's all ones and zeros, binaries, ones and zeros.
So binaries, ones and zeros. Talked a couple of different things about it as well.
A few different methods of conversion.
Good. So what were the different methods of conversion?
All of binary to decimal.
Yep. So just binary. We'll just say that that's a straight up normal third year binary that everybody knew when they started. What other representations did we look at?
There's two-bit notation.
2 is
Close.
complement.
Yeah. 2 is complement.
2 is complement, signed bit notation.
Awesome. 2 is complement. We also talked about signed bit. And we also talked about another one.
Floating point representation.
Floating point representation.
Which is to do with the mantis and X.
It was just to do with what?
Mantis and X.
Yeah. Now, really, before we discussed anything to do with that, we talked about something. But I got you to do that. Remember the 4 points.
Oh,
Just realised
2
that's
states.
video they're all.
2 states.
Right, we talked about why binary.
Because they're the same
So binary is what?
2-state numbering
Yeah.
system, because the computers are 2-state
2
machines.
state. Computers. 2 state. What's our 2 states in binary?
1 and 0.
1 or 0. 2 states in computers?
On or off.
On and off. So why do they use them? Well, the 1 can represent the on state, 0 represent the off state, simplifies a lot of the calculations that need to be done in computer systems. We talked about some of the advantages of using binary in a computer system. Do you remember any of them?
Less arithmetic rules.
Yep, less arithmetic rules. Good, that actually covers them all, Caleb. So that's addition, multiplication, subtraction, and all the rest of them. Because we only need to learn 1 plus 1, 1 plus 0, 0 plus 1, and 0 plus 0, instead of all of the 10 different numbers that we know if we were working in maths.
Can we take
Any other advantages?
pictures of it?
I take a picture then, that's a good idea. Any other advantages of it in terms of electricity, charge?
No degradation.
Yep, not affected by voltage degradation, not affected by voltage degradation. Now, if I was offered tips, it's not anything that's not normally asked in the exam, but it's useful to know anyway. So not affected by voltage degradation, less arithmetic rules, and it's easy to store the states in backing storage, or easier anyway, than storing 0 to 9 different states. Okay, so that was our first lesson. We talked about why computers use binary numbering system, talked about the advantages. Disadvantages are that it's difficult to read and spot for mistakes. Then we moved on and we just kind of did a reminder of ourselves of how we represent numbers in binary, how we take a decimal number and put it back into binary. Then we started looking at different representations because we looked at how we could represent negative numbers. Now, what was the disadvantage of the signed bit notation?
It gives you less range.
Yep, so reduced range, why?
In case you don't really count the first number, case only either means positive or negative.
Good, exactly, yeah. So we sacrificed that first bit to tell us whether it's positive or negative. A 1 would tell us the number's what? Negative. 0 would tell us it's positive. There was also another problem with that. Would you get that?
2 values for 0.
2 values for 0 and a reduced range. 2's complement took care of that. Yeah, because we could use all 8 bits in the range. After we talked about the negative numbers, we went on to talk about what type of numbers?
Real numbers.
Real numbers, right? So they're going to come up and they'll ask you about real numbers in the exam. Real numbers. A programming would say a single variable. Yeah, in fact, the exam would even say a real number as well. So there's two parts. This is where we get our daft gang insignia to remember the two of them.
Mantissa and exponent.
So it's made up of two parts, awesome. So we've got the mantissa and we've got the exponent. What represents what?
The mantissa.
Yeah, nice one guys there, yeah. So that's the actual number. And the exponent tells us,
How
Many
many
places
places?
decimal moves.
yeah, move the decimal. So it tells us how many places we want to slide that decimal number along to get a really precise number. So, we come up with the wee daft phrase, because they're really difficult to do, that floating point is a nightmare. What does the mantissa directly affect? The accuracy, right? So the mantissa is going to affect the accuracy. What's the exponent going to directly affect? The range. Awesome. So a positive or a negative effect on them. You increase the mantissa, you increase the accuracy, you decrease it, you decrease the accuracy, and so on. So that was numeric representation. What did we look at after? We've seen how to represent the different numbers. Didn't do file fonts, come back to that in a minute. After that, numbers, we looked at
ASCII, isn't it?
ASCII, yeah, we looked at representing of text. So we looked at two different representations, didn't we? We looked at ASCII and we looked at Unicode. So, some of the things you can remember about ASCII or Unicode then?
ASCII's 7 bits, 8.
Yeah, so ASCII's 7-bit. Who wants to disagree or add a wee piece to that?
He said.
Extended ASCII, say.
Yeah, so we can get 8-bit is extended. If I wanted to work out how many different characters that could represent, how would you do it? 2 to the power. Yeah, so 2 to the power 7's how many?
128.
128 characters. Extended it, gave an extra bit, allows it to store 256 different characters. Very limited. Yeah, barely got any the hyphenated characters, never mind Chinese alphabet, Russian alphabet, and any other character-based languages. Unicode brought in 16-bit. So why bring it in? What do we need it for?
Store all languages.
Yeah. So we can represent more characters. Right, cars, and it equals more languages. So there's an advantage. Unicode can store more characters, can store more languages. There's a drawback to it though. What's the drawback?
It uses 4 bits per character.
More bits per character. How many more bits?
16.
Per character?
I mean, no.
2.
He uses another bit.
Right.
He uses a full byte, isn't it? So it's 8 bits more. It's double the memory. How would to remember it? 8 bits more or 1 byte more. So that was ASCII Unicode for representation of text. After that, we kind of went back to maybe another revision piece we had done, which was really all the graphics calculations. So we'll leave a wee bit for graphics there, but the wee piece before that was the different memory sizes that we group into the different units we group them into. So what's the different groupings we do? What's the smallest unit of memory? Bits, yeah, so let's draw a big B. Bits,
Bytes.
bytes,
Kilobytes.
kilobytes,
Megabytes.
megabytes,
Gigabytes.
gigabytes,
Terabytes.
terabytes. Alright, so I want to see people writing that down in the exam, yeah? If I give you a number in terabytes, and I tell you to put it into bits, every step along this, it's like being in the train, you need to pay for how far you're going to travel, yeah? If you took a number in terabytes, what's the effect going to be in your end number?
Very massive.
It's going to be massive, yeah, but not a massive decimal, a big massive whole number. If you go the other way and I give you a big number of bits until you put it in terabytes, it's going to be a smaller number. Maybe even if I told you to put 1 bit into terabytes, it would be like the most ridiculously small decimal number, wouldn't it, with exponentials at the end of it. Every step costs you how much money?
1024.
1024, apart from what's there.
Bits to bytes.
Yeah.
Bits to bits.
Guys that are getting questions wrong in that, how long does it take to draw that? 2 seconds. It takes 2 seconds to just go 1, 2, 3 stops. Okay, that's 1024, 1024 and 8. Okay, so you chuck away marks for kind of simple stuff that you can practice, and you'll see them. You'll get 3 markers on these graphics types questions. Right, graphics. We looked at 2 different representations of images, which are...
Bitmap, vector.
Yeah, so we'll get vector and bitmap. How are bitmaps stored?
A list, like each every single pixel individually.
A list
Their colour
of every pixel,
and their colour.
store its colour. Yeah, we could sit for ages and draw out a grid of 1,000 pixels. I get different coloured pens and write blue, red, green, 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 and sit for ages just writing them down. And we looked at that, we talked about it, we did compression, which is the next part. How are vectors stored?
Oh, I think 2 bits.
Yeah, a list of objects. Because everything on that board there is an object. There's a sofa, there's some letters. Yeah? What do you need to store about each object? What's different about every object?
It's attributes.
Yeah, and its attributes. Now, what really shows you understand something is when you can give examples. What examples of an attribute, of an object rather, would they
X
say?
and Y coordinate.
The X and Y coordinate,
Gradient.
the gradient of it, but what's some other more obvious ones of it?
Colour,
Shape,
size, shape,
colour,
Line thickness.
line thickness,
border.
the shape,
Size.
shape, size. Yeah, good. All good examples.
Size.
We talked about the negative, if you want to call it that, for the bitmap, in that it saves the full screen. And I'm going to put anyway there. If you add more objects to a bitmap, if I put more things onto this board, saving it as a bitmap, would it have the same memory as if the board was blank?
Yep.
Yeah? Because it's just going to say white square, white square, white square, white square. And when I add more stuff in, it says, right, well, now it's a black square. Does it take more memory to save a black pixel over a white pixel over a blue pixel, green pixel? No. Every pixel's got the same amount of memory requirements in a bitmap image, yeah? So this one, if you add more objects in there, let's say we save this screen as a vector image, and I'm going to add more stuff to it, what's going to happen to this vector image's memory requirements the longer I'm working on it? Increase, why?
You adding more detail? Or more
Adding more detail, I'm adding more
data.
what?
Object.
Objects, right, let's start using objects for that and make sure, guys, that was one thing at homework that people weren't putting in. Give me examples of things where possible. So we talked about the representations of them. We said how bitmaps are resolution independent. Or sorry, did we say the resolution independent? We didn't. What did we say they were? For bitmaps?
Free.
Fixed resolution, yeah, mixed up. So which means they can't scale up clearly and accurately. You can scale them up, but they'll look as if they're made out of Minecraft blocks. They'll be all a total mess. Whereas the vector one, if you scale it up, you increase it, it will display accurately and clearly. Because it's a mathematical representation, really. So it could just scale up the length of a line. So it'll be no different. What did we say that was? That was the word that's I put here. What did we say that was then? Resolution what? Yeah. Independent.
Resolution Scotland.
So that means that if it's going to display a monitor, a printer, whatever it is, whatever the resolution is in the device it's going to display on, it will fix itself to that resolution because it will change because it's independent of the image, whereas the bitmap's fixed to the resolution of whatever you originally create it as. The last wee bit we talked about that applies to all graphics, and it was what? Compression. Nice one, Caleb. Compression. Now, what was the 2 types of compression we spoke about?
Lossy and lossless.
Lossy and lossless.
Lossless indeed. Lossy harsh.
Now, before I forget, what's the advantages of compression?
Advantage of
Yeah, less
quicker downloading speeds.
memory requirements,
Quicker
Backing
downloads,
storage would be a better thing to say. Less memory requirements.
quicker upload and download
Yep,
speeds.
so quicker to upload and download.
To send them quicker.
Yep, same idea. Save them on Facebook. Pages will load quicker that use them. Yep, so less
Sure.
memory required. You can fit more images, more videos. So we'll just say more space for other stuff. And when I say space, I should really say more backing storage. You've got more space left over, more backing storage to save other things. The negatives, quality.
Quality. Pure no quality.
It could be reduced. It could add in parts to the image that weren't already there, or the video, whatever you're compressing. Look, if you took a 24-bit colour bitmap and reduced it to black and white, that's a method of compressing it. It's not going to look as good, is it?
Yep.
Forgot that we just did that there. 24-bit
True.
equals what? Yeah, that. True colour. Forgot that bit. Okay, so we know the advantages of compression. There's two types. There's lossy and there's lossless. Which one is going to lose no quality of the image?
Less.
Lossless, right? Because we're not losing anything. No quality loss. And the quality will be reduced. Possibly not always to a visible standard, but there will be parts of the image sacrificed to make it smaller. We then spoke about 3 different graphics formats that could be saved as.
JPEG.
Right, so you said JPEG. Is JPEG lossy or lossless?
Lossless. Say.
What are pegs?
Pegs, you can lose them.
Right, always losing pegs off my washing line. Come in and they're like attached to my shirt and stuff like that. Right, so
Bring my
JPEgs.
boxers.
JPEGs are lossy. JPEG stands for.
Joint polytographic experts.
Good, have a read over that. How many bit colour depths do you use?
34.
And it's 24 bit. Right, get different types of JPEGs. Not technically only 24 bit, alright, but for the purposes of the exam it's 24 bit. What was the lossless?
Yeah.
Monochrome.
Yeah.
GIF? Yeah? We'll talk about that one in a second. GIF, purposes of the exam is 8-bit colour depth, alright? Just pretend that it's true, because you can get 24-bit GIFs and whatever else as well. Tend to be for their animated GIFs and so on. We spoke about one other image file format that was neither lossless or lossy.
Monochrome.
Monochrome. TIFF. You could argue it's lossless because there's no effect on the image quality, but it's not lossless because it's what type of format?
It's not compressed.
It's not compressed, so it's a raw format.
Raw.
Raw. There's one extra wee piece of information you need to know about this raw
G-star.
TIFF.
G-star.
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 Right, jeans?
G-star.
Nonsense. Yes, it allows a transparent colour. So you can store a transparent colour when it comes to TIFF file formats. Other stuff that we've not got on there, important things, obviously the actual conversion of binary 2's complement. Remember the cheat for 2's complement? Negative in front of the 128 at the beginning and add it up just as we've seen before. And the graphics calculations, practice them as much as possible because they're 3 markers and I guarantee you right now they'll be in your prelim and they'll be in the exam. And they'll definitely be in the end of the unit test. Right, any questions about any of that? Do you want to go over?
Snap.
Yes, I know.